It's certainly a pleasure to talk to you today. I know that a lot of the high school teachers and other teachers that I had when I was growing up in Philadelphia were very influential in terms of getting me to where I am now. And so I'm very grateful to that. So I'm happy to talk to you today, and hopefully something about what I'll talk about today will be useful to you. So today I'm going to be talking about the interior of the Earth and some of the dynamics that go on there. And we live on a planet that has a wide diversity of geology that's observable at the surface. We have great continents that cover a big portion of the surface. We have deep trenches in the oceans. We have giant mountains. It's a very interesting place. And that geology that we see at the surface is a manifestation of a long time history of dynamics that we can just visualize at the surface of the planet. So there's a lot of kind of Earth history that's recorded in the rocks at the surface. And it also takes great forces from the interior of the Earth to produce that. So we can kind of break this talk down into two things that I'm going to try to link together. One is geologic change at the surface. So the surface, as I said, has all this geologic change that we can observe in the mountains and the rocks and the landforms that we see. And then it takes great forces that arise from the deep interior to produce this at the surface. So the main question I'm going to try to answer is, how is the surface geology, which is so interesting to us, how is it linked to the deep interior? Okay? So that's what I'm going to try to talk about today. Okay. So I'm going to come back to this diagram a couple times, and I'll explain it now. So here's our main question: how is the surface geology linked to the deep interior? And you can think about this as what we'd ideally like to know is the entire history of the Earth throughout the depth of the mantle. Okay, so let me explain that. So if you go along this axis, I've got time going from the beginning of the Earth to the present day. This is now. That's what we see now. And then this axis is deep in the mantle. So this would be the surface of the Earth, and this is the core mantle boundary at depth. Okay, so you're going down. And so what observations do we have that can try to place constraints on this? The first is that we have observations of geology at the surface. Okay, and then we can record that we have some observations. I don't know if somebody talked to you about how they do this, but we have observations of when certain events happened on the surface of the Earth. Okay, and we have a lot of information about the surface of the Earth now. And then we also have information by kind of piecing together the geologic record. We have information about what the surface of the Earth was like in the past, going back towards the beginning of the Earth. Okay, so we have a lot of information from the surface of the Earth, and then we want to go deeper. So to go deeper, often we use seismology. And I think Barbara Romanowitz talked yesterday, and she probably showed you some pictures like this. Sorry? Yeah. Pictures like this of images of the interior of the Earth right now. Okay? And so we have a lot of information about the mantle structures as a function of depth in the Earth right now, but we don't have any information for the past for those things, because obviously we can't do seismic tomography for past times. We don't have the data for it. So, okay, so what do we want to do? What can we do if we want to fill in this part right here? It's basically, we need to understand, it's the domain of models. We need to build models or construct models that will tell us about the interior of the Earth as a function of time. So we have information here, we have information here, and we want to try to fill in this part. Okay. So I think that Francesca gave a great introduction, because I think she said, and maybe you heard this before, that all models are wrong. And that's basically true, because we can't actually know what, and we'll never know what the interior of the Earth was doing as in the past times. But we can develop useful ways to think about the interior of the Earth. And those useful ways can Well, we really just want them to be useful for our understanding, and then they should be testable in some ways. So I'll give you an example of some models that are useful. Okay, so in fact, this George Box made a famous quote, "All models are wrong, but some are useful." Okay, so that's what we're going for here. And he was a statistician. So a model is basically a representation of some physical process. And it should be useful for understanding the process, and it should be testable in some way. So here's a very simple model. This is a beaker, and you put corn syrup in it, and then you have a burner down below that's going to heat up the bottom. Okay, and so if you run this movie, okay, it's heating up, and then you can see this I guess the bottom heats up, and the material gets less dense because it's hot, and then it rises to the surface. Okay, and we know the interior of the Earth is hot, and so we think maybe something like this should be going on. Okay, there are other and so this is an example of what we call convection. So convection is basically the transfer of heat from one place to another by motion of the material itself rather than thermal diffusion or something. So if I heat up the bottom of this table, do that same experiment with the burner on the bottom of the table, then it would heat up and it would take some minutes before I felt it at the surface. The actual table isn't going to deform and move the heat up. But in some materials it does that. And so how can we understand that? So the process is called convection, and you can observe convection in like a lava lamp. If you've seen a lava lamp, and it's hot down below, and then the material rises up. Okay, so that's a good model. And a lot of people have kind of an image of the mantle. In fact, this is one of my first memories of studying convection. We were in a hotel room, and we had a lava lamp in there for some reason, and it was just interesting to see the material move like that. So that's one example. Another is miso soup. Miso soup is you can see the actual convection happening in miso soup. You can see these lines here, and if you get a bowl of hot miso soup and watch it cool, you'll see this. That these are basically cold downwellings. That the surface is cold, and the cold material is dense, and so it sinks down, and it doesn't bring any of the starchy material with it. So you see it draws these lines. And then the upwellings come from below, and they bring the starchy material with it. So it's really interesting to watch that. Okay, now I will, okay, so we have this image of convection. We'd like to study it more and build more sophisticated models than lava lamps and miso soup. And that's what I'm going to do now. This is an experiment that I was involved in when I was an undergraduate. And what we did, I just got this job at the university doing this. And what we did is we had this big tank of corn syrup, like this big, like this, and about that deep. And it was heated from below. So we had this water system tank that heated the bottom. And then you see those plumes, like I showed you in that beaker with the Bunsen burner. And what we did to image it, and this is in the 90s, so we didn't have the same kind of good imaging we have now. What we did is we took a projector, we shined it through the tank, and it's broken. Okay, well, I'll try this, and hopefully it won't be too many variations in sound. Yeah, we shined the light through the tank, and the shadows of these plumes showed up on a screen in the back. And so these are images from that screen. And so little by little, the tank got hotter and hotter, and you can see the characteristics of the convection are changing. That here you have big wide plumes with big heads to them, and here they get narrower and narrower. And what's happening is the whole thing's getting hotter and hotter. And so the character is really changing, and that's interesting. So how can we describe this? This is another model, and this is the only equation that I'm going to show you. But basically, you can describe convection in terms of this one quantity. It's a dimensionless quantity called the Rayleigh number. And it's the ratio of a whole bunch of different dimensional parameters that when you cancel out all the dimensions, then you get a single number, which is called the Rayleigh number. And you can see some of them like density, gravity, the depth of the fluid. The viscosity is very important. And so if you take the ratio of all these parameters and apply estimates, and I wrote the estimates here for the mantle, you get a number that's like 7 times 10 to the 7th, which I guess is 70 million. And then if you go through the numerical theory, or the physical theory that is behind this, then you find that convection should occur if the Rayleigh number is bigger than this number 657, about 1,000. So the mantle is way above that number, so it should be convecting. Whereas if you did it for this table example, the Rayleigh number of the table would be very small, so it would not convect. So that is a useful model for how you can determine if a material is going to convect or not. Okay. Let's see. Right, so here are the Rayleigh numbers that we estimated for our corn syrup tank. And you can see the Rayleigh numbers getting bigger. So this is telling us that as the Rayleigh number gets bigger, then these plumes should get less like, they should get thinner with time. But the Rayleigh numbers here are similar to what we have in the mantle. I said it was 70 times 10 to the 7th. Here's 4 times 10 to the 7th. It looks, the convection, you have a lot of upwellings and stuff. And that's very different than at least the convection that we see at the surface of the Earth with these big plates. And so what's different about that? So we can do, and here's another, okay, so I'll get back to that about what's different about the mantle than a corn syrup tank. But if we want to do this in a computer, okay, it's a lot simpler. And in fact, after that experience working in the lab, since then I've only worked on computers, really. So if we want to do this on a computer, then we need to take the equations, and I guess I said that was the only equation I was going to show, but here are 3 more, and I put them up there because I like that. These are the equations for conservation of mass, conservation of momentum, and conservation of energy. And these are like 3 fundamental principles, basically. And these are expressed instead of, in a physics class, you have conservation of mass, and conservation of momentum, and you watch balls move around and stuff. These are expressed in a continuous media, so a fluid, basically. And so these are the fundamental equations of fluid mechanics. You solve these equations for some geometry, and this is just a box, and so we have a hot bottom and a cold top, and let's run the movie to see what the convection looks like. There we go. You can see the blue stuff is sinking and the hot stuff is rising, just like in the laboratory experiment. And you have things that look a little bit like plates here. So now we're moving towards something maybe that looks like plates. If we want to do this in a sphere, then we need to solve these things not in a box, but in a sphere. And so there's certain ways that people have developed to make a mesh that has a spherical shape. Because all the boxes on here, if you brought it to the pole, they would all go to be really small, and that's not good for the numerics. So you can take these 2 shells and put them together. That's one way to do it, kind of like a tennis ball, or if you know the sport of baseball. Baseballs are constructed that way too. Okay, there are other ways to do it, and a lot of people. And another thing is that you can have one computer solve this side and one computer solve this side, and you can even break this into smaller pieces, and you can have these giant computers solving the equations of motion in these in this kind of baseball-shaped thing. Okay, so we can do that, and it gets actually quite complicated. So we need to make some major simplifications in order to get this to work on a computer. And so here's an example. This is a paper where they took a mesh that their computer could handle and made it even finer near the places where there's a lot of deformation. And you can see here it's very fine deformation. But this is a scale of 50 kilometers. So the resolution here is maybe a couple kilometers. And if you look at rocks in geology and fault zones, the deformation, the changes that happen are on the scale of meters or less. So you'll never get the full complexity of the Earth in a computer. You have to simplify it. So that's another thing to know. We'll always have less complexity than the Earth has. Okay, and then we have to make some major assumptions because we don't know, we can't go into the interior of the Earth and measure all the properties down there. So we need to make some major assumptions about what the interior of the Earth is like. Okay, and here's another, this is not a movie, sorry. This is just an image of a cross-section through the mantle of one of these calculations. And now you can see things that look like slabs here in a plate. And what's shown here is temperature. So these slabs are cold. They're sinking into the mantle. And you have hot plumes coming up from the interior. Okay? And so one of the questions, one of these fundamental quantities that's hard to estimate is the viscosity. It's like how stiff the rocks are. You have a feeling for like how stiff honey is or something like that. And basically, we need to have a measure of how stiff the rocks are. But one thing we know from materials like honey, if you put it in the refrigerator, it gets stiffer, right? So that also happens with rocks. So these tectonic plates are very stiff because they're cold. And it's similar to what's happening with honey in a refrigerator. Okay, but we don't know how stiff they should be, so we can try different things on the computer to see. And here's an example where we made them not very stiff, so sort of weakish plates. So they're not that much stiffer than the interior. And if you do that, you get deformation patterns like this. Now the color scale here is red is no deformation, green is very slow deformation, and blue is fast deformation. So you have these regions where you have fast deformation, and then you also have regions where there's slow deformation. So it's a little bit different than the Earth, because we see the Earth has rigid plates that don't have any deformation, and then on the boundary, you have a fast deformation. So let's make the plates much stiffer. If you make them very stiff, then you have the whole surface just kind of frozen up. And that isn't like the Earth either. That's actually more like what Venus is doing, or Mars, where the surface is very old, and it's probably convecting underneath, but the surface is frozen. Okay, and if we go to something intermediate, then we get the deformation localized on something that looks like a plate boundary, and very slow deformation in the middle. So this is something that's more like the Earth. So we need kind of something intermediate. We can't make it too stiff but we need to make it somewhat stiff to get plates. Okay. So this is the most Earth-like model. So we can proceed like that. Okay. So what do you get when you put that in? And now this is another model. This is kind of the core, and you'll see convection happening in the sphere. Okay. And, yeah. Okay, so here are the plumes coming up. And what you're going to see soon, it's going to go into slow-mo. Here's a plume coming up, and watch this plume. It's going to deform the surface, and now you have subduction. And there's the plate subducting into the interior. And it's going to happen in some more places, like this. And you can see that once you have these slabs sinking down, they're big, heavy things, and they push a lot of material out of the way. And so they really control the flow patterns that happen in there. It's not just plumes coming up, that it's the plates themselves are driving the flow when they start going down. So that's a very, very important part of how convection happens in the mantle. And now we have things that look like a subduction zone on Earth, kind of how we think subduction zones look on Earth. Okay. So now we want to look at the surface. Here's the surface deformation of a model that's sort of like that. This is by another group. And you have these zones of fast deformation, and you have continent-like things that are moving around on the surface. Okay. So what we would like to do is compare that to observations. So now we're ready, our models are ready to start comparing to observations from the Earth. What observations from the Earth do we have? Well, we know where the continents were in the past and how they moved around. And so this is we call it a tectonic reconstruction. So the continents used to be together in Pangaea, and then they started splitting apart, and these rifts formed, and then they moved apart. There's certain rates and things like that that are associated with all this motion. So we can start to compare some of the observations that we can make in tectonic reconstructions. These are coming from the geologic record to the rates that are happening in here. And I came up with 7 different measures of this that I could directly compare to this. So does anybody have any thoughts about things that we could compare between the two? Just observations that you can make on a time-dependent model like this. I came up with 7. I can show them. You could compare the spacing of the boundaries, so how big the plates are. Is that comparable? The length of the plates and the length of the plate boundaries and also their width. There's a certain width to this plate boundary. And so that's something that might be detectable in the geologic record. How long-lasting are these plate boundaries? The rates of deformation, do they migrate across the surface? And what type of boundary it is. Like here, the subduction zones are distinguished from the ridges. And we see both types in here. Okay. All right, so now I've gone through and I've tried to explore along this. We have the tectonic history and how it's related to the interior. And so we've kind of expanded in this direction, starting to go deeper. And now I want to start taking information from seismology and try to go this way on it. Okay. Yeah, can we understand at least mantle flow for the present day? And I've done a lot of work on this. And basically what we do is we take a seismic tomography model like this, which I think Barbara Romano showed you, and we convert these seismic velocity anomalies into a density. So we infer that the blue stuff here, which some of it we can trace to a subduction zone, is cold, and the red stuff is hot. So it's a very simple conversion that we do. And so we're saying that that's cold, that's hot, and then how should the flow look for the present day? Okay, and this is what you get. So now you see I've taken those seismic images and I've converted it into density. This is mantle density anomaly. Blue stuff is dense, red stuff is light. And I've put that into the computer, run the code, and the arrows is basically what you get. So let me explain it. The colors here in this plot are showing the vertical velocity. If it's blue, it's sinking down. If it's red, it's rising up. And so under South America, at 1,000 kilometers depth in the mantle, the model predicts that the material should be sinking. And then beneath Africa should be rising. And then I've drawn cross sections from A to B and C to D. So here's A, here's B, and these are cuts through the mantle. And so you can see there's this material, there's that slab that's subducting beneath South America. It's sinking down and it basically drives the flow away from it. And similarly here in C, we have C to D, that cross-section through Africa. We have this upwelling happening beneath Africa. Okay, and then here's a cross-section through the entire mantle. This is kind of going almost through the equator. So this goes through Africa and the Pacific on this side. You can see you basically have 2 large upwellings, one beneath Africa, one beneath the Pacific. And that's the arrows going up. I think Barbara Romanovitz also talked about these LLSVP zones at the base of the mantle. They're kind of continent-sized things. They show up as red things on the seismic tomography, but they might be very dense. So there's one upwelling above the African one upwelling above the Pacific one, and then downwellings in between. So here's the downwelling. Let's see, this is on the South American side of the world. This is in the Western Pacific, under Japan, basically. subducting here. Okay, and so now what we want to do is compare to present-day observations. And there's a lot of different ways that we can do this. I'll just mention one, because I don't really have time to go into all of them. But one is that we can try to use the models to predict plate motions. And because that's really what we observe at the surface. And these are the observed plate motions, and the colors represent kind of the relative speed of the plate. So you can see the Pacific, the plates in the Pacific are moving very fast, and all the other ones are moving slowly. And that's basically, we can get the directions of the plate motions pretty well. This is the predicted plate motions by the model. The velocities are, the relative velocities are pretty good, and the directions are fairly well comparable also. So we can kind of have some confidence that we have an idea of how the mantle is flowing for the present day. Okay, so now we want to go back in time. We'd like to we have some understanding of how this works, where the mantle is flowing right now. How do we go back in time? And that's hard, because these models are set up to run from, you give it the density structure and the viscosities, and you run the model, and it goes forward in time. But we don't know the structures that were in the past, right? We can't go back in time and say, have tomography here, and then run forward to the present day. We can only guess at what the structures were like. There's certain things about the Earth that might make that easier to do, and this is an area of active research. But one of the things is that the locations of subduction in the present day locations of subduction is in the gray, but if you look at where subduction was in the past, then they're shown by the different colors, and different colors indicate age. So at least for the last 300 million years, the locations of subduction were shown here and here. They haven't moved that much in terms of the grand scale of the Earth. That hasn't swept across the entire Earth. You mostly have this ring that goes from pole to pole and around basically the two LSVPs. It goes around Africa and it goes around the Pacific. And it's migrated a bit around that kind of belt, but it hasn't changed that much. So if we drew a cross-section across the equator like this, then we would still see something, even in the past, we'd still see a zone of subduction in these two sides and upwelling in between, above the two LSVPs. So that indicates maybe some stability, at least for this 300 million year time scale. Okay. Another thing that might indicate some stability is if we look at the locations of volcanoes that happen away from the plate boundaries. We know that subduction zones and ridges have a lot of volcanism associated with the plate boundaries. But there's some volcanoes, and I lived in Hawaii for several years, so I'll show a picture of Kilauea Volcano here. That's an example of a volcano that's happening in the middle of the plate. It's away from the edge. So Hawaii would be up here, and what we've noticed is that if you reconstruct the locations of where all these hotspots are, all these locations of intraplate volcanism, a lot of them tend to form around the edges of these two big LSVPs. So that might also, and this is going back in time. So some of the volcanism is here, especially in the green dots, were a large igneous province, basically a big flood basalt that put a lot of volcanism on the seafloor or on continents, and then the continents got moved. But if you reconstruct it back, a lot of them end up on, or were erupted on the edges of these LSVPs. And so this indicates that maybe these LSVPs have been stable for a very long time. Okay. All right. So what picture of the mantle can we think about in terms of keeping the LSVPs stable and plumes coming up from the edges? And this is some calculations that a grad student and I were working on just recently. It's Bjorn Hein, and he published the paper last year. But basically he said, okay, let's assume that the subduction on the surface is always putting slabs in the mantle in the same place, and so we drive a flow like this. Then where do the plumes happen? And what you find is that the plumes, the material runs along the core mantle boundary and it pushes this material, this hot material up until it hits the LSVP, and then the plume rises up. And you can see here the next one is forming here, and it comes up. And so maybe this is something, a model that might be useful for explaining this, this kind of stable mantle flow with plumes coming up from the edges of the LSVP. Okay. So yeah, here's an example. So the idea is that maybe we have a fairly stable belt of subduction all around the LSVPs, and if you keep that stable, and it's a good question of why would it be stable, then it would sweep the plumes up against the edges of the LSVP, and then they would go up. Okay, so kind of like this. Okay, so a good question is for how long could this have been stable in Earth history, and that's something that we're working on now. Okay, so I've started to fill in the interior of this diagram, moving back in tectonic history. We think we understand some of how the convection can lead to plate motions. And then we've done the present day mantle flow, and then starting to move backward, kind of making the assumption that the basic pattern of this flow was fairly stable over at least recent geologic time. Okay. All right, so it's nice to be able to compare this to observations, and this is an active area of research right now. So I'll just describe one way that we're thinking about this. If you have a piece of rising mantle, like we think is happening beneath Africa, if it rises up, it should produce a topographic deflection at the surface. It should push the surface up. The amplitude maybe is up to about 1 kilometer. And of course, we know that the continents are high, and there's other reasons for that. But this, kind of in the background, we expect a dynamic topography that looks sort of like this, with low over the downwellings in the Western Pacific and South America, and high in the Pacific and Africa above the upwellings. Okay. And now, if we have this, okay, back in 250 million years ago, the continents were assembled in Pangaea, and just moving it forward, if we assume that this background pattern is, the background mantle flow pattern is stable, then this prediction of the dynamic topography should also be stable. And so the continents, when they go forward in time, then they move off this high place and move into the lower areas. And so they should subside as you go. And that should be something that could potentially be observable in the geologic record. So that's something we can test. We can compare against models like this, which is back when, this is from 105 million years ago. This is a Paleo geographic reconstruction. So you have the continents assembled where we think they were, and also there was flooding in some of the areas of the continents. And that comes from the geologic record. Okay, so we can compare things from the movie, the predictions from the movie, to the actual observations. Okay, and then that's an active area of research right now. Okay, but we have to be careful because there's a lot of things. Basically, we're looking at a comparison of sea level to the continents moving around, and there's a lot of things that can affect sea level. So every time we make these comparisons of geological observations to mantle flow models, then we have to take into account that the geologic observations, and in fact that the models are probably wrong, and the geologic observations are complicated to interpret. That there's a lot of factors that go into changing sea level. For example, here's that process that I described. You have a mantle upwelling, uplifting the surface. That would indicate a sea level drop if you had that going on. But let's say there's a lot of islands a lot of volcanism in the bottom of the oceans. That happening at the same time, that would make sea level go up because you're putting all that material in the ocean, and that would also look like a sea level rise. So all these things are happening at the same time, and so it can be challenging to interpret these things. Okay, so just to conclude, the models like this one can help us understand mantle flow and how it links to geologic observations at the surface. These models, as we've said, are probably wrong, but they can help us to understand mantle flow. We think that the plate tectonic, we think we understand at least somewhat how plate tectonic behavior can arise from a mantle flow model. We have to make sure that we get the viscosities right of the plates, and there's various ingredients that kind of have to go into the model to get that to work, but we think we're starting to understand that. And we can understand somewhat the patterns of present-day mantle flow, at least on very large scales. So the next challenge for us is to understand mantle flow for past times and to really link it to the geologic record. So we can ask, how stable is the mantle flow pattern? I've presented some evidence that it's fairly stable, at least for the last 300 million years, but there are arguments about that. And can we relate this past flow to geologic observations? And doing this will hopefully be able to answer somewhat this question. Okay. So I hope some of this was useful to you, and I'd be happy to take some questions. Thanks.